Rudewright Academy. Learn it, teach it, remember it. What if one structure gave you the sum of any range and let you change any value both fast? Normally you pick one to be quick. The segment tree refuses to choose. Let me show you. Here is an array of numbers, 8 of them. We want to answer a range question fast, like the sum of positions 2 through 6. But we also want to change any single value just as fast. Do one of those well, and the other usually falls apart. The segment tree quietly does both. The plainest way to sum a range is to just walk it, adding cell by cell. 4, 5, 11, 14, 21. It works, but every single query has to touch every cell in the range. On a big array, that gets slow fast. Now here is a smarter idea. Pre-compute the running totals, the prefix sums. Then any range becomes a single subtraction, prefix of 6 minus prefix of 1. That is constant time, basically instant. But here is the catch. Change one value and every total after it is suddenly wrong. You have to rebuild the entire tail. Here is the turn. Instead of pre-summing the whole array, we pre-sum every block. Neighbors into pairs, pairs into fours, fours into halves, and the halves into the whole. Stack those blocks up, and together they form a tree. From the leaves to the root, it gets smaller at every level. Each parent is simply the sum of its 2 children. So we build from the bottom up. The first pair, 5 and 2, makes 7. The next pair makes 5, then 9, then 9 again. Those combine into 12 and 18. And the very top holds the total of everything, 30. Now let us actually answer a query. We start at the very top and walk down. At every node, we ask one simple question. Is this block fully inside the range, fully outside, or straddling the edge? If it is fully inside, we take the whole block. If it is fully outside, we skip it completely. And if it straddles, we open it and ask the same question of both children. Let us trace it on our real range, positions 2 through 6. The pair 2 and 3 sums to 5, fully inside, so we take it. The pair 4 and 5 sums to 9, also inside, take it. And the single position 6 is 7, take that too. That is 3 blocks, not 5 cells. And together they add up to 21. Now what if we change position 5 from 3 to 10? Only the blocks that actually contain it are now wrong. And those blocks all lie on one single path, from the leaf straight up to the root. So we walk that path upward, adding the difference, plus 7 to each node. Position 5 becomes 10, its parent climbs to 16, then 25, and the root lands on 37. One path, a handful of nodes, no tail to rebuild. Here is the whole query, just 9 lines. At every node it asks one thing: how does my block compare to the range? We start at the root, the block 0 through 7, which straddles the range, so we open both halves. The left half, 0 through 3, still straddles, so we open it again. The pair 0 through 1 falls fully outside, so it returns nothing. But the pair 2 through 3 is fully inside, so it returns its sum, 5. On the right, 4 through 5 returns 9, and the single 6 returns 7. Add them up, and 3 blocks give us 21. A few things to watch out for. First, decide once whether your ranges are half open or closed, and then stick with it. Second, when a block straddles the edge, you must open both halves because opening just one will quietly miss cells. Third, give the tree room. Allocate about twice the array size, or 4 times to be safe. And last, the combine operation has to be associative. Sums, minimums, and maximums all work, but something like count distinct does not. So why is this fast? The height of the tree is just the logarithm of the size. For 8 elements, that is only 3 levels. And a query touches at most 2 blocks on each level, one fully inside and one straddling. So the total work is about 2 times the height. Both queries and updates cost around log n steps instead of walking the whole array. On big data, that is an enormous win. And it is not just sums. The very same tree can find the smallest element in a range, or the largest, or the greatest common divisor of everything in it. It can even update a whole range at once, not just one cell. All you change is how 2 children combine. The tree itself stays exactly the same. So here is the whole power of the segment tree. Any range query is just a few pre-summed blocks glued together, and any update is one single path, from the leaf to the root. Pre-summed blocks stacked into a tree, both queries and updates living in log n. Want to keep learning? Come find us at academy.rudewrite.com.